Welcome one and all to Colloquium. Today's speaker is Professor Vivienne Baldassare. She's been here since 2020. So she's as well, let's start at the beginning. 2017 is a PhD, and that was at University of Michigan. And then after that was a postdoc. She was an Einstein Fellow at Yale. And then from that position, we were lucky enough to land her here at Washington State University. Her thesis topic and the focus of her subsequent research has been black holes in low mass galaxies. And there's, as you will shortly find out, lots of uncertainties and lots of ways forward as well to this interesting and really cutting edge frontier science. So thank you for joining your own faculty here and students and sharing this talk, which is called Measuring the Population of Massive Black Holes in Dwarf Galaxies.
Thank you. All right. I'm really excited to have the opportunity to tell you all about some of the exciting work that my research group has been doing on measuring the population of black holes in dwarf galaxies. So I just wanted to give a shout out to all the members of my research group. Chris Carroll is a postdoctoral fellow in our group who has a fellowship through the LSST Discovery Alliance. We have 4 PhD students in our group: Allison Acosta, Aaron Kimbrough, Alexander Messick, and Eric Wisleski, and undergrads Julia Jitkov and Juan Pena, and I'll be sharing some of their work with you today. So first, I wanted to talk a little bit about why we're so interested in looking for black holes in dwarf galaxies. So I'll touch on the elusive intermediate mass black hole population and also the black hole occupation fraction. One thing that we have learned over the last several decades is that every relatively big galaxy has a massive black hole at its center. So this is a video of individual stars moving at the center of our galaxy. And this is based on work that's been done at UCLA for over 3 decades now. So they're actually tracking the orbits of individual stars at the center of our galaxy. And this was Nobel Prize winning work a couple of years ago. Based on the orbits of these stars, we've been able to infer the presence of a black hole at the center of our galaxy that weighs around 4 million times the mass of our sun. And there's a lot of things I love about this video, but one of them is that it illustrates really well that when we search for black holes, we're searching for the influence that the black hole has on the stuff around them. And in this case, that's the gravitational influence that it has on stars in its immediate vicinity, but we can also look for its influence on bulk motions of stars or gas.
Vivienne, can I ask a dumb question?
Yeah, of course.
How do you see that? Isn't it all like kind of messed up and there's stuff you got to look through if you're looking at the galaxy?
So it's we have to use infrared observations because those are better able to cut through all of the dust and gas extinction in the plane of our galaxy. And then it also requires the use of adaptive optics. So yeah, in order to achieve the angular resolution that you need to do this, you need to use very sophisticated adaptive optics systems.
So these are Earth-based observations.
Yeah, this is from the Keck telescopes in Hawaii, which is, yeah, unreal. Yeah, actually, so the scale bar there is 1/10 of an arcsecond. So usually from the ground, we can only achieve maybe 0.5 arc seconds at best without adaptive optics, so it's really necessary. Okay, so every relatively big galaxy, like our Milky Way, has a black hole at its center. Of course, we can't do individual star orbits for other galaxies, but we've been able to infer this using other techniques. The situation is a lot more complicated for small galaxies or dwarf galaxies. So these are galaxies that are a few percent the mass of the Milky Way. So that's what I mean by dwarf galaxies. And for these systems, we know very little about whether they contain massive black holes like their much larger galactic siblings. So this is an image of the Large Magellanic Cloud, which is the closest dwarf galaxy to our Milky Way. It's orbiting around the Milky Way galaxy. You can see that it's kind of an irregular looking galaxy, so it doesn't have a nice spherical or nice spiral shape. And even though this dwarf galaxy is in our galactic backyard, we actually don't know whether the Large Magellanic Cloud has a black hole at its center. And in fact, there's even debate over where the center of this galaxy is. So it's hard to know where to look. And all we can say is that if there is a black hole here, it's not very active. It's very quiet. There are a few reasons why we care whether there are black holes in dwarf galaxies. And one of the big ones is that it may help us constrain how we think supermassive black holes form in the first place. So there's a lot going on here, but we'll walk through it. What is shown on the left are different black hole formation mechanisms. So most of these take place in the early universe, and there are different pathways through which we can form the seeds for today's million or billion solar mass black holes. So there's a few different pathways here. We'll start from the bottom. So this is called the direct collapse pathway, and basically says that the seed for today's supermassive black hole forms from the direct collapse of a really massive gas cloud in the early universe. So in this case, we would start out with a black hole that was already maybe 10,000 times the mass of the sun. Moving up, we could also have the seeds for today's massive black holes form from the deaths of massive stars in the very early universe. So this would be a more common process, but would leave behind a smaller initial black hole of maybe 100 times the mass of the sun. And then on the top, we have black hole formation through dynamical processes in star clusters. And this is unique in that we can form the black hole seeds at any point in our cosmic history, not just in the early universe. So all of these predict different black hole mass starting points. When we evolve through to the present day, that results in differences in the population of black holes in small galaxies. So these are a few different very rough diagrams for what we would expect in terms of the number of black holes as a function of black hole mass, the fraction of galaxies that contain a black hole as a function of galaxy mass, and then black hole mass versus galaxy mass. And the key thing here is that for massive galaxies, basically no matter how you form the initial black hole, everybody gets one. But in little galaxies, depending on how the initial black hole forms, you start to see differences, right? So there's differences in the fraction of galaxies that contain a black hole. There's differences in the black hole number density, and there's differences in the relationship between black hole mass and galaxy mass. So by studying this population of black holes in dwarf galaxies, we can provide some observational constraints for these black hole formation theories. Additionally, dwarf galaxies are really good places to search for intermediate mass black holes. So up until now, been talking about supermassive black holes. So these are the black holes upwards of 1 million times the mass of our sun. We also have stellar mass black holes. So these form when massive stars die and undergo supernova explosions. And then in between is this whole range of intermediate mass black holes where we don't have much observational evidence. And it is unclear whether these black holes don't exist at all. Nature just doesn't make them in that mass, or whether they're really hard to find. And so we've started trying to push in on this regime. So LIGO has started to detect some black holes of around 100, 150 solar masses, which is very exciting. And then dwarf galaxies, if they have black holes, we expect them to be in this range of 10,000 to 100,000 times the mass of the sun. So by looking for black holes in dwarf galaxies, we may be able to shed some light on this intermediate mass black hole regime and find objects in this mass range. One of the tricky things about searching for black holes is that they themselves don't emit any light. So we have to get creative in how we search for them. And for dwarf galaxies, the black holes that they contain are relatively less massive than the black hole in our Milky Way or at the center of a really giant elliptical galaxy. So they have much smaller gravitational spheres of influence, which means that they're harder to find. And so we can generally only find very active black holes in dwarf galaxies if we want to build up population statistics. And so we need to search for signatures of what we call active galactic nuclei, which are just black holes that are accreting material or eating at a very fast rate. And when a black hole is accreting rapidly, you get this disk of material around the black hole called an accretion disk. And that disk emits lots of light that is more easily detectable. So a lot of the work that I do is focused on searching for these active black holes or active galactic nuclei in dwarf galaxies so that we can understand this population of black holes in dwarf galaxies. All right. What are some of the observational techniques that we can use to find these active galactic nuclei in dwarf galaxies? So traditionally, a lot of active galactic nuclei, or AGN, are selected through their emission line signatures. So the light from the accretion disk around the black hole ionizes gas within the galaxy and produces certain emission line signatures that we can then detect when we take a spectrum of that galaxy. And active galactic nuclei are not the only things that can ionize gas within a galaxy. You can also get ionization from star formation. And so if we detect these emission lines in the spectrum of a galaxy, there are certain diagnostic diagrams that we can use to try to determine what is the source of that photoionization. So this is a standard diagnostic diagram in astronomy that uses the relative strengths of different emission lines, so oxygen and nitrogen emission lines to H alpha and H beta, to characterize the dominant source of photoionization in a galaxy as being due to star formation or active galactic nucleus activity or some composite combination of the two. And so this was from a work done in 2013, where they looked at 25,000 dwarf galaxies and found these spectroscopic emission line signatures for black holes in about 150 of them, which doesn't sound like a great percentage, but was actually a huge increase in the number of dwarf galaxies that we knew to have an active galactic nucleus. So this was a really good starting point to say that, hey, some of these dwarf galaxies actually do contain active black holes, but we may not be catching them all. So these diagrams were designed for more massive galaxies, and there's a bunch of reasons why they may not be as effective for dwarf galaxies and may miss some objects. Yeah.
I guess, what is the physical process that gives more emission from the accretion disk versus the star forming?
It just has to do with the ionizing spectrum. So you get a harder ionizing spectrum from an accretion disk than from star formation. So more higher energy photons. So one of these lines is theoretical based on the kind of maximum photoionization that you would get from star formation. And then the other one is an empirical cut, which again was made with more massive galaxies in mind. Okay, so this is one way that we find active galactic nuclei in dwarf galaxies, but they don't always apply for dwarf galaxies. So we might be missing some objects. The property of active galactic nuclei that I've been really focused on is variability. So the light from the accretion disks that surround these active black holes is variable over time. So this is a plot of the brightness from the center of an active galactic nucleus over time. So this plot spans about 8 years. And you get these fluctuations in the brightness from the center of the galaxy due to turbulence in the accretion disk. And so if you take many, many observations of a galaxy over time, you can look for these fluctuations and establish whether that galaxy has an active black hole or not. So I wanted to see if we could use this variability to find active black holes in dwarf galaxies that we may have missed otherwise. So variability, so changes in the brightness from the center of the galaxy over time, and other flares due to the presence of black holes called tidal disruption events might be able to help us find black holes in dwarf galaxies, measure their masses, and place some observational constraints on these black hole formation theories. So this just shows the brightness versus time at the center of a pretty nearby quintessential dwarf galaxy with an active galactic nucleus. And this one's kind of neat because you can also see variations here on short time scales. So now the x-axis is in hours. So smaller black holes, we think, display more rapid variation. So if we can have really frequent observations, we can also start to constrain black hole mass, which is really interesting. So I wanted to use this variability of active galactic nuclei to try to find black holes in dwarf galaxies. So I'll just show a little bit of what that looks like observationally. So in order to look for this weakly varying source on top of a host galaxy, we use a technique called difference imaging, which is where you subtract off everything that isn't variable and search for the things that are. So to do this, we take a whole bunch of images. So we might have hundreds of images of the same galaxy and construct a template image from the best frames. So the images that have the best resolution and the lowest background. And then we basically go image by image and degrade the template image to match the resolution of each one of those images one at a time, and then subtract the template from the individual image. And then from there, in all of those subtracted images, we would measure the light at the center of the galaxy and look for things that are variable. So,
Vivienne,
yes.
when you talk about the best frames, is this again an atmospheric problem? Is it ground based?
Yeah, so you would want to have the frames where your atmospheric turbulence was relatively low.
Because that get really high resolution pictures. But yeah.
Yeah, so you're really sharp images. So this is an example of a galaxy that's not variable. So on the bottom is just brightness versus time. The data is those little gray circles, and you can see those are the difference images. There's no features that stand out against the background, right? It's just noisy. So this is an example of a galaxy that does show variability, and you can see these bright and dark points that pop out against the background from the center of the galaxy. So we search for objects that have some variability, and then we also search for objects that have variability that is consistent with what we expect from an AGN or an active galactic nucleus. And so we do that by modeling the fitting the light curves with a damped random walk model, which has been found to be a good empirical descriptor of AGN variability, and then look at the goodness of fit of the light curve to that model. So again, on the bottom, we have our brightness versus time, and then the blue shaded bar is just that best fit damped random walk model. So I did this for about 35,000 dwarf galaxies with data from a survey called the Palomar Transient Factory, which surveyed a lot of the sky for over 10 years. And from this sample of 35,000 galaxies, found a couple of hundred of dwarf galaxies that had active galactic nuclei based on their variability. So these are just a couple of examples of galaxies that we found to have these variable active black holes. So these galaxies are both about 1% the mass of our Milky Way galaxy. So this variability search technique can find active black holes in dwarf galaxies. One of the really interesting things that I found was that most of these variable active black holes in dwarf galaxies would not have been classified as such by these optical spectroscopic diagnostics. So this is the same diagram that we saw before with the star formation region, the active black hole region, and the composite region. And then each of those points is one of the galaxies that we found to have variability consistent with an active black hole. And so most of these would have been missed by these other selection techniques that were designed for more massive galaxies. So we're finding active black holes in dwarf galaxies that are missed by other techniques, which is really important if we want to have a complete understanding of the population of black holes in dwarf galaxies. So a couple of my graduate students have done some really interesting follow-up work on this sample. So Messick analyzed Chandra X-ray observatory data that we obtained for 14 of these galaxies. So these are some of the dwarf galaxies that we found to have variability selected black holes. And Messick analyzed X-ray observations for them to try to look for additional evidence of the presence of active black holes. And so Messick found that 5 of the 14 galaxies we had X-ray data for had definitive nuclear X-ray sources, which is really strong additional evidence for the presence of an active galactic nucleus. The remaining objects in the sample were either weak detections or undetected, which could be reflective of much shorter bursts of black hole accretion or some difference in the accretion properties of these lower mass black holes. Erin Kimbrough has been studying the Hubble Space Telescope imaging of these objects. So Erin has modeled the structures of 8 of these dwarf galaxies that have variable AGN to compare them to dwarf galaxies with black holes selected through other techniques and to try to understand whether there's anything unique about these systems. So these are the Hubble Space Telescope images of these 8 dwarf galaxies with variable black holes. And Erin found a very diverse range of morphologies or shapes for these galaxies. So some are really irregular, some are kind of spheroidal, some have a little bit of disc or spiral structure, but most of them are best modeled by including a bright central point source, which could be the active galactic nucleus. And Erin actually just submitted this paper a couple of weeks ago. So Erin did a lot of work to try to look at these central bright point sources in these galaxies and determine whether they are in fact these accreting black holes or very dense nuclear star clusters. And without going into too much detail, basically Erin modeled what they would, what their masses would need to be based on their luminosities and colors if they were nuclear star clusters, and found that in general, their properties are much more consistent with active galactic nuclei. So that's the plot on the left, is what their masses would have to be if they were nuclear star clusters. And so they don't tend to agree with the general population of nuclear star clusters. Looking at the brightness of these central point sources, they really interestingly sit right between the AGN and dwarf galaxies that are selected using spectroscopic techniques and dwarf galaxies that have central bright point sources that are not AGN. So these variability selected AGN might just be fainter black holes than the ones that are selected through optical spectroscopy. So these were 2 really interesting studies that were follow-up on that larger sample of variable black holes in dwarf galaxies. Okay, so one of the things that we've seen is that these different ways of selecting black holes in dwarf galaxies don't necessarily agree with one another, right? So the objects that we find when we search with variability are different from the objects that we find when we use optical spectroscopic diagnostics. And there may be some selection biases associated with these different techniques that we don't fully understand yet. But if we want to know what is the full population of black holes in dwarf galaxies, then we need to understand the selection biases associated with these different selection techniques and study how they overlap, right? So this is how we can obtain our best observational constraints on the population of black holes in dwarf galaxies. So Eric Wisleski has been studying these selection biases associated with different active galactic nucleus identification techniques. So what Eric did was to compile a sample of over 700 dwarf galaxies that were found to have active black holes in a bunch of different ways. So it was a very non-homogeneous data set, but Eric took these 700 galaxies and applied a consistent set of active black hole selection techniques to all of them, and then studied the overlap. So there were 9 different selection techniques that we looked at, including variability, X-rays, optical spectroscopy. And this is just one plot that shows where all of these different populations fall on that original spectroscopic diagram. So you can see that for dwarf galaxies that have active black holes found through X-rays in the bottom center, not all of them are selected through optical spectroscopy. So we went through this for all of the different selection techniques and tried to see what the overlap was. So what we found is that there's generally little overlap between the objects that are identified by different techniques, and that any one active galactic nucleus selection technique only finds a fraction of the overall population of active black holes in dwarf galaxies. So the best technique was actually one that looked at helium-2 emission. And that one only identified about half of the sample as having an active galactic nucleus. So this is just a bar chart showing kind of how different objects are identified by different techniques, and showing that there's not a lot of overlap between all of these different selection methods. And this is really important because it emphasizes that for dwarf galaxies, we really need a lot of multi-wavelength data and a lot of different ways of looking at these objects to capture the full population of black holes. And so these results are really important to compare to simulations of black hole formation and growth in dwarf galaxies, and for revising the fraction of black holes in dwarf galaxies that you might get if you're only using one selection technique. As the next step in that work, Eric is comparing the galaxy properties between all of these different subsamples. So these are spectral energy distributions where you take a lot of multi-wavelength data for your object and basically come up with a model for the stars and the black hole and how all of those different components contribute to the overall photometric observables. And from this kind of modeling, you can estimate things like star formation rate, dust extinction, metallicity of your galaxy, the AGN power. And so we'll be looking at how all of those different properties might play into what techniques are effective for what galaxies, basically. So trying to link these different selection techniques with galaxy properties and see if we can say that X technique doesn't work for galaxies that have a lot of star formation, something like that. So I'm really excited that our group is a member of the Young Supernova Experiment, which is a time domain survey using the Pan-STARRS telescopes in Hawaii. So this is a survey that has been operating since 2020 and surveys about 1,500 square degrees of sky in 5 different photometric bands. And it goes deeper than some other very prominent repeat imaging surveys. So we're sensitive to smaller variability in dwarf galaxies. And we have these 5 different photometric bands, so we're able to look at variability across the electromagnetic spectrum. So this is really useful for the kind of work that I do, where we're searching for these small variations from dwarf galaxies, because we have this really deep imaging. So MESIC has been carrying out a search for variable AGN in dwarf galaxies in this young supernova experiment data. And this is an example of a light curve for one object that has this AGN-like variability. So this will really build on previous studies because we'll be sensitive to lower levels of variability. So we'll be able to find smaller and weaker black holes. And we're also able to study variability at different wavelengths. So these are different bands from G, which is around 4,000 angstroms, to Z band, which is around 8,000 angstroms. So we're able to look at variability at all of these different wavelengths. So we should, MESIC has identified many new AGN in dwarf galaxies, and we'll be able to compare these to past variability analyses to study decades-long variability of dwarf galaxies. We're also able to measure the active fraction in this sample. So look at the overall fraction of galaxies that have an active variable black hole as a function of galaxy mass. And this is another really important point of comparison for models of black hole formation. So MESIC finds a few percent variability and maybe some drop off with galaxy mass. So another thing that we're able to look for with these repeat imaging surveys are tidal disruption events. So these are one-off flares that occur when a star wanders too close to an otherwise quiescent black hole. So that's shown in the little cartoon on the left. You have a star that happens to wander within the tidal disruption radius of a black hole. And basically the star gets torn apart. Some of that debris will fly off into space. Some of it becomes bound and will accrete onto the black hole. So when this happens, you get a really bright flare called a tidal disruption event. And this is complementary to the analysis I've been talking about so far, because these black holes are quiescent, right? So they weren't active before, but now we've seen this unlucky star get torn apart. So we're finding a complementary population. And by modeling the light curves, so the brightness versus time for these events, you can also get an estimate of the black hole mass, which is really useful. So one really exciting event that we found in the young supernova experiment data is this tidal disruption event called AT2020 NEH. So this is the tidal disruption event that occurred in a dwarf galaxy. So on the left is just an image of that dwarf galaxy. There's a Hubble Space Telescope image of the center of that galaxy, where you can see the bright source at the center and some nuclear star formation around it as well. And then on the right is showing that this galaxy was formerly identified as just having star formation based on its optical spectroscopy. So there was a flare in this object that we found with the young supernova experiment data. And based on the modeling of the light curve, we're able to infer that this black hole is around 10 to the 5 solar masses, so 100,000 times the mass of the sun. And again, this is in a dwarf galaxy. And the rise time in the light curve is what is constraining for the black hole mass. So a fast rise time is what you expect for a lower mass black hole. So these are just all different photometric bands, and you can see the flare from this object. So based on this light curve modeling, we're able to estimate the mass of this black hole and then look at how it compares to the galaxy properties. So these are just plots that show the black hole mass versus the galaxy velocity dispersion, so the speeds of the stars in the galaxy, and then black hole mass versus galaxy mass. And these are also important constraints for models of black hole formation. So this object is the star on both of these plots. And from this data, we find that it agrees really well with the relations between black hole mass and galaxy properties that we find for much more massive galaxies. And Allison Acosta has also been analyzing tidal disruption events with our young supernova experiment data. So this is Allison's light curve for the tidal disruption event called 2020 OPY. And Allison has been analyzing this object to measure the black hole mass, the disrupted star properties, and the galaxy properties. And hopefully we'll submit that in the next couple months. All right, in the last couple minutes, I want to talk about another survey called the Mirian survey, which is a survey to identify 100,000 new dwarf galaxies in our relatively local universe. So one challenge in computing the fraction of dwarf galaxies that contain an active black hole is that we don't have a complete census of all of the dwarf galaxies in our local universe. So measuring galaxy masses relies on knowing how far away those galaxies are. And because dwarf galaxies are so faint, and spectroscopy to get redshifts or distances for these galaxies is resource intensive, we don't have distances for a lot of potential dwarf galaxies in our local universe. So Mirian is a really unique imaging survey that will obtain redshifts for 100,000 nearby dwarf galaxies. And Mirian is named for Maria Mirian, who was a 17th century entomologist and studied and archived bugs and tiny things. And so we named our Mirian survey of tiny galaxies in honor of her pioneering work cataloging little critters. Okay, so basically what Mirian does is use two custom designed medium band filters to estimate redshifts for dwarf galaxies that are within a certain range of redshifts. So if you have galaxies that have spectroscopic emission lines and these galaxies fall within a certain redshift range, then those objects will pop up as really bright in these two different medium band filters. So Mirian will be sensitive to galaxies in the range of about 10 to the 8 to 10 to the 9 solar masses out to redshifts of around 0.1. And we anticipate detecting 100,000 new dwarf galaxies in this mass and redshift range. So this illustrates the medium band filters a little better. So if you look at the plot on the right, it shows a spectrum of a dwarf galaxy, and you can see how these particular emission lines will be picked up in these two filters for a certain range of redshifts, basically. So using these custom designed filters, we'll identify 100,000 new dwarf galaxies, which we can then use to study a host of different things, including the population of black holes. And so that's what Aaron Kimbrough will be working on next, is finding black holes in this large, complete sample of dwarf galaxies. Okay. And so our observations for Mirian are nearly complete, actually. So we have a DR1 data release 1 catalog already of objects that we can start looking at. And one of the really neat things that we have found so far is that the Mirian dwarf galaxies seem to exhibit a very wide range of H-alpha emission, so hydrogen alpha, which generally reflects star formation in a galaxy. So you can see here that some of these galaxies have really compact star formation. Some of them have really diffuse star formation with little knots. And it'll be really interesting to see whether this diversity relates at all to the presence of a black hole in any of these galaxies. Okay. So just to wrap it up, the present day local universe population of black holes in dwarf galaxies is a really important constraint for models of black hole formation. We need to use multi-wavelength indicators of active galactic nucleus activity in dwarf galaxies in order to get a complete picture of that population and provide the best constraints on the overall fraction of dwarf galaxies that contain a black hole. So we can't just use one of these selection techniques. We really need to bring them all together to have a complete understanding of this population. Variability is one way that we can find active black holes in dwarf galaxies that are missed by some other techniques. And there's a lot of exciting work that we're doing now with the Young supernova experiment. And I expect that we'll make a lot of really exciting progress in this area in the next few years, thanks to that continued Young supernova experiment data and our new sample of dwarf galaxies from Mirian. So there. Thanks, everyone.
Thank you. Any questions? I have a warm-up question, which is variability.
Yeah, also on the detection methods here, so that graph of all the 9 detection methods you have, are there a significant portion of them that have been all confirmed by every single one of your methods?
There was, I think there were like 20 or so of the 700 that have everything. Yeah.
So that, I guess a follow-up to that is, how many of those need to go right for you to confidently know that there's an active galactic?
Yeah, that's a good question. So how reliable is any one method? So I will say that most of the sample was detected in by more than one technique. So that's encouraging. And then there is some data inhomogeneity, like not everything had X-ray, for example. But generally, it kind of depends on the technique. Like if you only have X-ray emission and it's relatively weak, then that could be from a couple of different things. So it depends on what your sources of contamination are, really, as to whether you can trust a given.
It almost seems like a very galaxy to galaxy kind of analysis.
Yeah.
Just apply this general law.
Yeah.
Really seems individualized.
It's the tricky thing, because what we're really trying to get at is this population, and if there's so much individual variability, then yeah, it's a challenging puzzle, but.
Kind of a physics question, because you use optical wavelengths for the variability studies. If you could magically have a telescope that went to a different wavelength, what wavelength would you pick?
So because the accretion disk emits primarily in optical UV, that's kind of the ideal range for studying that variability. But I do think ultraviolet would be really interesting. And we also do know that there is X-ray variability from these systems, but it's observationally tricky because you need a really, really sensitive high resolution X-ray telescope. So that would be like the dream instrument, but don't think it's gonna happen.
Good, and just remind me about this helium-2 feature. Like, where is it in the spectrum and why is it effective at picking out AGN?
Yeah, the helium-2 feature is around 4,600 angstroms. So relatively blue, but still visible light. And it's a fairly high ionization potential emission line. And so it's generally only produced by things that have fairly hard ionizing spectra. So really energetic ionizing photons, like inactive galactic nucleus. So that's why it's a pretty good way of finding these things, provided that you have an optical spectrum that is basically sensitive enough, long enough exposure times, because it can also be kind of a weak line relative to the hydrogen transition.
Right.
Yeah, great talk. Early on, you mentioned one of the motivating factors was to look for these medium range sized black holes. And you might have kind of addressed this where I was noticing, but I did notice one place where you said like 237 GN, and they're all like 10 to the 7, so I guess 10 million and larger in terms of their mass.
Oh, so
Have you seen the smaller?
those masses were galaxy masses. So usually the black hole is about 1,000th the mass of the galaxy. In most of those systems, we don't have direct measurements of the black hole mass itself, but they're really good candidates for follow-up. If we were to get higher cadence monitoring, we could potentially constrain black hole masses that way, or look for spectroscopic features to measure black hole mass. So with just variability alone, we're identifying them, but then there are ways that we can follow up to get more direct measurements of the black hole mass. But yeah, those were galaxy masses. So think 1,000 times less massive for the black hole. Peter?
Is there any way to spatially resolve images of the tidal disruption events, or are they so far away that you only see like these spectra?
So these are photometric observations that we use for the light curve, but generally they are so far away that we wouldn't be able to spatially resolve anything going on at the center. So we just see the flare. We can take spectra, which also have unique features, but nothing is close enough that we would be able to really do any spatial resolution.
How well it's been a long time since I've done dark matter simulations. How well do the current n-body simulations predict the black hole distribution? And do they need gas dynamics in there? Presumably they do.
I mean, I think the issue is that for our simulations, it depends a lot on like how you seed your galaxies with black holes. And so there are so many decisions that folks can make there.
That doesn't fall out of the simulation. That's something that's still put in, like star formation used to be.
Yeah,
Okay.
yeah. And so you can, I mean, some simulations will just start all black holes at 10 to the 6 solar masses. And so those aren't very constraining, but we're starting to get to higher resolutions where folks will input realistic criteria for when something will collapse into a black hole. And so there's been a lot of improvement there in the last few years, but there's still a lot of range of what you get out at the end in terms of the black hole population.
Let's thank Vivienne for, one more, Maria.
So, how far would you go from the active fraction to the total equation fraction?
Yeah, it can be, it's tricky, especially because, when you start to get to the lowest, the faintest dwarf galaxies, you don't know if you're just not sensitive to black holes of that size. So what we try to do is, at least control for magnitude distribution and then compare to the higher mass galaxies where we know the occupation fraction is 1 and see if there's any change. And so we kind of do it by comparison to the higher mass bins.
Let's thank Dr. Baldassare.